Good afternoon, everyone. My name is Ramakrishna, and I'm going to make this presentation on my data mining course project. The title of my project is Solar Power Generation Forecasting. So, my project includes power generation forecasting, predictive maintenance, and performance analytics of the solar farms. As you know, solar energy is a promising source of renewable energy harvested by solar power plants. The objective of this project is to apply data mining techniques on solar farm historical data to predict future electricity generation, detect fault equipment, and determine maintenance needs of the solar plant. The dataset used for this project is solar power generation data, which is taken from Kaggle. It includes solar electricity generation and weather data. The project will involve exploratory data analysis, regression analysis, ensemble predictive modeling, and it will calculate key metrics to evaluate the model. As the world is transitioning to renewable energy, solar power generation has become a very rapidly growing industry. With the increase in reliance on renewable energy, it is crucial to forecast energy generation capacity very accurately. Advanced data mining techniques can extract insights from sensor measurements, condition indicators, weather data, and more. And the results of this project could significantly enhance the efficiency and reliability of solar power generation. So in this project, I'm going to do these three things: power generation forecasting, predictive maintenance, and performance analytics. Coming to the dataset. So the dataset is taken from Kaggle. The name of the dataset is solar power generation data. So it has two different types of data present inside this whole dataset. One of them is solar power generation data and weather sensor data. Both of them are time series data generated at the plant itself. Solar power generation data is generated from the solar inverters that are present in the plant. So it has some key features like DC power, AC power, and the daily yield, which is aggregated over the day. And the weather sensor data also, it is time series data with some features like ambient temperature, module temperature, irradiation, which are deciding factors for solar power output, because these features impact the solar power generation. Now coming to the process that I followed for my project, so it includes data collection from the Kaggle, then exploratory data analysis, which includes analyzing the data, plotting the graphs, observing the distributions, and also identifying correlations to tag the important features that are needed, followed by feature engineering and data preprocessing, which includes I performed the initial preprocessing, which includes encoding the variables, okay, and also replacing the missing values, and also normalization. And after that, for the data preprocessing, I split the data into training and testing sets, and also made the data ready for the training the model. Then after that, once the data is ready with the preprocessing, so the model selection happened. And here I have taken a set of models to work with my data. So some of them are linear regression, random forest, gradient boosting, extra trees, and other boost. So each of this model is trained on the data that is preprocessed. So, and also in my preprocessed data, the important features that are considered are DC power, AC power, ambient temperature, module temperature, and irradiation. Then coming to the model evaluation, so for each of these models that are generated, so I considered some of the evaluation performance metrics, such as R squared, mean absolute error, root mean square error. Then based on these metrics, I identified which models are performing better. In my analysis, I found that random forest and extra trees are outperforming all other models. Then at the end, I tried to do a ensemble approach, where I did both simple ensemble and weighted ensemble to build a comprehensive model. These are some of the data distributions that I checked when I was doing the EDA, and also the fields that I'm going to consider. Now, coming to the model's performance. So I found that you can see that linear regression, random forest, gradient boosting, extra trees, and other boost our models are tested. So here I found that linear regression, gradient boosting, and other boost are performing poorly. You can see from their R2 scores, which are less than 0.5 or around 0.5. But the models random forest and extra trees have performed really well with R2 score of 0.9. So because of this, so for my ensemble model, I choose random forest and extra trees as the base models for creating my ensemble model. So, and finally my ensemble model performance is almost similar to the random forest model with a R2 score of 0.923. Then coming to the second part of my project, which includes the predictive maintenance for identifying any faults in the power generation. So here the same the process followed is collecting the data from using the same data that I collected from Kaggle, then exploratory data analysis, which we have done before. But here for detecting the anomalies, some feature engineering had to be done. So here I have created some new features that could be indicative of maintenance needs, such as the rate of change of power in the output, or the frequency of the anomalies in the data, because these will help us to identify the anomalies. And then I have trained isolation forest model with with the data consisting of the engineered features. Then finally the model evaluation is done. So the isolation forest models for anomaly detection have been trained for both the plants. In the anomaly column, a value of -1 indicates an anomaly, while a value of 1 indicates that it is a normal behavior. Now, once I performed this model evaluation and saw the output, so there were 664 anomalies identified in the plant 1 and 669 anomalies identified in the plant 2. So this information can be used to investigate the cause of these anomalies, which may indicate equipment malfunction, or maybe it might require some maintenance. So that's how it helps. And in the next slide, I have actually plotted, shown the output of the model where anomalies are there, and also I have plotted the anomalies in the graph. Then coming to the last part, which is related to the performance analytics of the solar farms. So here performance trends are identified, yields are compared, and what is the best performing inverter, I have identified that, and also found some correlation between environmental factors and power output. So here I found that the yield of plant 1 is around 6.6 million, and yield of plant 2 is 6.5 million units. Plant 1 has a slightly higher yield than plant 2. And also found the inverter efficiencies, and we also found which inverter has the highest efficiency in plant 1 and plant 2, and which inverter has the least efficiency, so that this can be looked upon why those inverters have least efficiency. And also showing some correlation statistics for AC power. The correlation between DC power and environmental plant 2 is as follows. Okay, AC power, daily yield, total yield, all of these are presented. The strongest correlation with DC power or with irradiation module temperature and ambient temperature, which indicates that these environmental factors have a significant impact on the power output of the solar panels when seen for the data 2, power plant data 2. So the output of this with this project, we are able to forecast the power generation data and also identify the anomalies, and finally see some analytics regarding the plants. And these are the references that I have used. Thank you, everyone.